Howdy folks, Mr. Reed here, and welcome to One More Question. So what we're going to do today is look at greatest common factor, and I'm going to do it for three-digit numbers. So I'm going to consider this a medium level of question. Basically, if you can do this and follow along with it, you should be good in any case because it's pretty general. You do the same thing every time. So if you'd like to see a reasonable middle level / good understanding case of greatest common factor, you're in the right place. Let's get to it. All right, so the numbers that I'm going to work with this time are going to be 396, 462, and 588. I'm going to see if I can factor these reasonably well on the fly in front of you. So I'm going to start with the 396. So the first thing that I usually do this vertical line thing. If you prefer the tree method, please go for it, and that would be appropriate. So let's go ahead. It's even, so 2 goes in. That's going to leave me with 198, which a 2 goes into that. That's going to leave me with 99. A 3 goes into that, leaves me with 33. A 3 goes into that, leaves me with 11. And those are all prime, so I'm done the prime factorization of 396. All right, next up we have 462. So a 2 does go into that. That's going to give me 231. Now, this one's probably the first one that I've come across where I don't just see something right away, but then I see the 231. Knowing your divisibility rules is really helpful. So in this particular case, if you sum your digits, 2 plus 3 plus 1 gives you 6, which is divisible by 3, which means that the entire number is going to also be divisible by 3. So I know 3 is going to go into that. It's going to go in, so it's going to be 70 plus another 7. So that's 77 times. And so now, even though this is kind of an awkward number, this one, because I know my 11s, so you get 11, 22, 33, 77. I know 11 is going to go into it. It's going to go in actually, I'm going to put the 11 first. It's going to go in 7 times, and so that will give me another prime factorization because 11's prime, and so is 7. So that one's done. I'm going to go to my last number, which is 588. So again, it is even. So that will go in. That would be 300 minus 6. So that would be 294. All right. So next up, that is also even. So 2 goes into that, and that would be 150 minus 3. So that's 147. I say the right thing out loud. I'm not going to record it. There we go. 147, and then I have 3 will go into that. There'll be 150 would go in 50 times, so 1 less than that is going to be 49. And then I know 7 goes into 49 and leaves me with a 7. Whew, done all my my dividing and factoring, so that's good. This should be smooth sailing from here. All right, now these are my 3 lists. So I didn't really explain where I was going with this, so if you've seen the mild video, you probably saw that I used a prime factorization in order to come up with a way to identify the greatest common factor quickly from there. It may not be the fastest method for my last example, which was 30 and 40. You might be able to identify that it's a 10 pretty quickly without really getting into something like this. Now, what I have here is what I think is the most efficient method to do this by hand, because now all I have to do is look for things that are in common between the prime factorization of these 3 separate numbers. The fact that it's 3 separate numbers has no bearing on the method, so it works the exact same way as with 2, other than it has to be shared between all 3 of them. So all of them have 1, 2. So there I'm safe to take a 2 from all 3 of these. The middle number, the 462, does not have another 2. So I can't use the 2 basically from either of the outside ones. You don't have to cross them off, but I'm just going to remind myself that I've talked about them. All 3 of them do have a 3, so that's good. The middle one does not have another 3, so we can't use that 3 there. The 11 that's on the first one, the 588 does not have an 11, so that is not going to be a common factor. The first one does not have a 7, so we can't use the 7s from the other ones either. So what ends up happening is we can see that the 2 is shared between all 3 of the numbers, and the 3 is also shared between all 3 of the numbers. So what do we do with the 2 and 3 prime factors that are shared? Well, we can make a bigger multiplied number with those together, which would be 2 times 3. And so we would have, for these particular 3 values, a greatest common factor of 6. Now that's a pretty low number. It just so happens that these 3, since they don't have a whole lot shared in their prime factorization, the value that will go into each and every one of these ends up being, as I said, relatively low. So if they had a little bit more, it could be higher, but that has nothing to do with how big the numbers are necessarily. It has everything to do with what kind of prime factors are shared. So that can be applied for any of these questions. Do a prime factorization, pull out all the things that are shared between your numbers, multiply them together, and that's your greatest common factor. If you found that to be helpful, like, subscribe, and as always, take care, folks.